All right, and with that, I guess I'd like to welcome you officially tonight. Welcome to my basement. Never thought that my basement would be the site of one of these, but unfortunately, it is what it is. These machine learning workshops were of great success prior to our little COVID adventure, and had a great response. And we wanted to figure out a way to try to continue them, despite the fact that we're not able to meet in person. So we appreciate you joining us tonight. I think we'll have 3 different speakers: Brian, Chris, and Dave Holmes. And if you have any questions, feel free to interrupt either over the mic, or feel free to use the chat window as well. So with that, who's going first? Is it Brian?
I don't believe so.
Oh.
I think I'll go first.
All right.
I can wing it if you want.
No. Okay, so I'll start sharing my. Oh, you got to enable screen sharing for participants, so I can share my browser window.
Sorry. Now do you see it?
Yep. Okay, so all right, can everyone see this? So open browser.
Yep.
So, okay, so it's going to be pretty easy to do these notebooks tonight. The first thing you need to do is go to colab.research.google.com. And you'll need to, I don't know if it'll require you to have a Google account or not, but if you do, if it does, make sure you sign in with one. Does anyone have any issues with having a Google account? Nope. Okay. So this is the welcome window. Getting to these notebooks is going to be pretty easy. On the window here, you see lists of different ways you can access a notebook. Click on the GitHub. And then in this bar, you'll just type SMNIEEE. And that'll search, that'll go to our GitHub repository for Southern Minnesota IEEE. And it'll find all the notebooks we have available. You can look at the ones from the first session, second session, but if you scroll down, you'll see session 3. So click on session 3/0_introduction. And that notebook should pop up. It's pretty easy. Anyone have any issues with that? Okay. So welcome to tonight's talk. In this particular session, we wanted to cover some details on something we kind of glossed over at the last one, which is training, testing, training, validation, and testing of data sets, so that you set up your regression or whatever machine learning model you have, and use the data you have efficiently to get the best results. I'm not going to go verbatim through the sections here. You can read through them if you want. The key to this is that we've started out with some basic regression, linear, logistic, penalized regression, and have showed how to fit a model to a given set of data. But how do we do that in a way where our model now becomes useful at making predictions about the future? So down here, what's the difference between this and what we've done before? Well, the keys are broken into 3 pieces. First, the data needs to be used to generate the model. So it needs to be split up and sectioned off so that some of the data is used to create the model, but then we need data to test the model with. think of it like setting aside or holding off data to pretend that it's new data that we want to see what the model does with it. So before we just mentioned training and testing, which is easy enough to think about. You take your data and you split it into 2 chunks. But really the best way to do it is to do what you see in this first picture, which is split your data into 3 pieces: training, validation, and testing. So as I was just mentioning, sorry about that, I was checking the chat window. You take the data and you split it into 2 pieces, and then you have the test set, which is a small portion, and you have the training and validation piece, which is the larger piece. But then the training and validation piece gets split again, and the validation section is what your model is optimized on. So you run the training on the bulk of the data, you use the validation to check the accuracy of the model, and then you can iteratively improve the model again and again on the training data and continue to check the errors that result from the validation data to know that you're getting a better and better fit of the data or the model to the data. Once you've gotten to the point where you feel that your model is a good fit, at the very end, you run your test data. And what that does is tells you roughly how good your model will be now that you've gone through the whole iterative process of training and validating it. So why do we need these multiple checks? Well, this is one of my favorite quotes: all models are wrong, but some are useful. Ultimately, our model is designed to not tell us about the data we already have, but to tell us about the data that will come in the future. We want to be able to make predictions, and that's the whole point of this work, is to be able to make predictions about data that will be generated. Sometimes the data will be given to you in chunks. Sometimes it could even be real-time data being passed to you sample by sample. So taking the approach of training and validating and then testing the model across any of the machine learning paradigms, you get an ability to really refine your approach and your model while also making sure that your data is not being used too strongly. And what do I mean by that? I mean, you don't want to overfit your data. So your data can be influenced by a couple of factors. Actually, I put 3 in here. First is bias. Think of bias as how much your model's expected value differs from the actual population of data's expected value. And then you can kind of think of variance is if your model fits the data well, variance should kind of look like random noise around the data or around the model. And then ultimately, you have to be careful about overfitting. And Dave Holmes is going to go into more detail on what overfitting is. But ultimately, you don't want the model to too closely track the noise and the biases in your data. You want it to represent the underlying features without fitting exactly to the data you have at this moment, because that's not the goal of the model. So the big question is, how do we split our data? Well, as you can kind of guess, you want to split it up into chunks where the majority of it ends up with the training data set. So first, what I think most people do is you take your data and you split out your test sequence, the final hold off data. And that can be anywhere 10 to 20% as an estimate. And there's a lot of ways to refine it. And I think Dr. Holmes will go into that a little more. And then you take the data, the large chunk of data that's left, and you split out that into your training and your validation data. And that can be done a number of ways. You can split it once and iterate on your training data and check with your validation data. Or you can do different forms of what's called cross-validation, where you iteratively split up the data and validation into separate chunks and then test it or try it, you iterate, and then you re-split it up again into a different set of chunks and make sure that the model's still converging the way you want it to. So that's kind of the background on what we're going to cover today. Is there any questions from anyone before I switch it over to Dave Holmes? No? Okay. So once Dave's done, then he'll come back to me and we'll kind of go through some hands-on stuff where we play with a little bit of data and look at how the splitting of the data can be done just in a notebook with some simple tools that anyone can access and some data that's available on the internet. So at that point, I will stop sharing and let Dr. Holmes take over.
So let's go ahead and hopefully everyone's in their browser. You've been to Colab already. You're gonna go down to the file menu and you're gonna open a notebook. In this case, again, GitHub, hopefully will list, SMN, sorry, SMN-IEE. And you'll go down to session 3, overfitting 1. And I'll give everyone a chance to do that real quick. So I think Chris actually set the stage perfectly for this whole thing. No questions. I don't see any, which is fine. I think Chris set the stage for this really well. What I'm going to do is I'm going to do some sort of background justification about this issue with overtraining and what it is and all that stuff. And we're going to do this through an example. So everyone should be able to see my screen. I'm going to have you guys follow along. For those that weren't heavily involved in the first two, let's take just a minute and cover Colab. Colab, the main thing is each one of these boxes are often called cells. You can see I can click on different cells. And there's really two types of cells. The first type of cell is text or instruction. And so you can see that I have some text that we're going to be talking about overfitting, underfitting, and the bias variance trade-off. And this particular notebook is a collection of several articles that I reference. And it's really about justifying why we're going to get into these training, testing paradigms. Often, particularly to someone who's not done a lot of this, they develop a model and it works really, really well. Everyone gets super duper excited. But unfortunately, a well-trained model using simple metrics actually gives very poor performance in the real world. And that's the issue of overfitting. So we're going to go through that. So those are the text kind of fields. Right below it, one that's probably a slightly different background tone. In my case, it's a gray tone. These are boxes that have Python code in it. And if you were in the first two, you saw this. This is called IPython Notebook. And you can do it through Jupyter, which is how we've done in the past. And now we're just doing it here. So as a reminder, the things in these gray boxes are code. The way you run them is you either click on the play button, or while you're in the box, you hit Control and Enter together. So let's just go ahead and jump right in. So everyone should be looking at this box here. This is box number 3. It basically talks about the libraries we're going to use. And if you go back to workshops, you will see that we used many of these libraries before. So NumPy is a way of building arrays of matrices of data, or arrays of data. Matplotlib will give us some plotting so we can see charts. And then scikit-learn or sklearn, as you can see here, gives us all those tools to build models. And we're going to be building linear regression models. You can see that there. So I'm going to have everyone go ahead and click play. It will give you a warning saying, hey, this isn't part of Google. That's okay. We're not doing anything, but you're going to hit play. And you're going to see it's going to spin around. And then it's going to execute. That means it's done. And I am going to pause here and just see if anyone that didn't work for anyone. So it should look the same. There's been no output there. That's okay. Just want to make sure everyone's running. Okay, I think we are. Again, stop us if not. Now, we're going to do this in a regression model. Remember, regression is a way of fitting a function. So there's some underlying function, in this case, a true function, and we're going to see if we can take data points and fit a model to it. And it's a very straightforward model. You can see, and I'll just do a little Python review here, that def is referring to a function. So we have a function that will take our input values x, and in this case, it's a cosine of 1.5 times pi times x, and then it returns that list. And so I can use true function to give me actual values of the function that I'm trying to do. Now, we don't, in real life, don't know that function, but in this case, we do because we want to just demonstrate it. For those of you who haven't done a lot of programming before, whenever you talk about random numbers, and we're going to talk about random numbers in terms of noise, you often seed that random number generator. That makes sure we're all getting the same answer. If you want to try and get a different answer or use different data points, you can change the seed, but it won't look the same. So if you put in a seed of 0, like what's there, everyone will see the same random numbers. Seemingly not random, but in fact, pseudo-random, we'll say. And we're going to say, we're going to create 30 samples. These are essentially 30 observations of our function. So the way that we do that is we have our value, our input, which is a number, and we're going to collect 30 of those numbers. And we're going to take those x values, and we're going to put them into our true function. And then on top of that, we're going to add random noise. This random noise is, it's normally distributed. We don't have to go into the details of that now, but we're going to add random noise. So, and then we're going to plot it. This will do an XY scatter plot. And so if everyone just wants to hit play on that box right there and scroll down, hopefully people are doing okay. Essentially, I have taken 30 random values between 0 and 1. I have calculated the true function and added noise to that. And given that you guys all saw the code, you know it's a sinusoid. It might look like a sinusoid. That's not really the point here. So I'm going to start to speed up a little bit in case if someone has a question, they should stop us. But I don't want to kind of belabor any of these points. So now, given the samples, we're now at the next box of code. Let's put a line to this. Obviously, a line's not very interesting. We already see that there's a pattern that's not a line, but let's try that. And so we're going to say this is a linear model of degree 1, which is a line. And we're going to say we want to create a polynomial that will be fitting, but the polynomial is only degree 1. So again, it makes a line. Now, you can go back. This link is here just to refer to linear regression. Linear regression is an optimization technique to fit something to a line or a polynomial, some sort of a linear function. And so we are going to build a linear regression model, and we're going to put that in a pipeline. So we're going to say, given my linear regression model and the polynomial features that I want, which is a first order polynomial, let's go ahead and fit the model. So any sort of these model things in sklearn all have a fitting function. And this is the optimization engine that takes the inputs, in this case x, it takes our inputs, and our known outputs y, these are our observations. So it takes these points here, and it's going to fit a model to that. And once we get a model, it's going to calculate the mean squared error. And I don't have the equation here, I apologize, but essentially the mean squared error is how much error we have between our model and our actual data points. So let's go ahead and run this box right here. And as it's running, I'm just going to take a look at the rest of the code. So I'm going to choose some points here, and I'm going to predict these points. Let's take a look right here at the bottom. So we have the points, the samples are in purple. Okay, and I fit a line to it. It makes sense. That looks like a line. And every point on the line has a corresponding real point. It turns out there's quite a bit of error there. You can see that. There's a lot of variability. So we really didn't do a very good job fitting, and that's reflected in the mean squared error of 0.41. So there's error there. Now, it's not surprising that a line didn't do a very good job. Perhaps we want to look at something like a second order polynomial. So here, this next block of code down here, all I've really done is change the degree to 2. So it's a standard second order polynomial. And if you hit play, you can see we're starting to get a much better fit. So now the distance between the dots that are blue, which is the model, and the dots that are purple is quite a bit smaller. And that's reflected then in a much smaller mean squared error. So now you guys get to play, and I'm going to stop talking for a minute. You go to this next box and you insert your favorite polynomial degree. Stick in some number you like. And put in a 7. Remember, you have to play that box that executes that 7. And then this next line of code, or this next box of code, just runs that model for you. This happens to be my 7. I'm doing pretty well. So I'm going to give everyone a chance. Choose one. Let us know how it's going. So I'll open up the floor to observations. Given what we're seeing is more better.
Oh, I just did 4 and that looks pretty good.
4 looks pretty good, okay. So I'm gonna do 15. Take a look at 15. We're kind of rocking it. Like I'm kind of a winner here with 15, right? It's looking really good. Now, this is really weird though, as you look at this. I did a 2 and my mean squared error was 0.05 and it looks pretty good. 13 looks wonky. Maybe someone wants to, I can show 13 so we get to see what maybe that one looks like. Anyone got an idea why 13 might look wonky? Where are my even odd function people? Maybe that's our issue. But here's the crazy thing. My number here when I was doing 2 is pretty small and there's some variation. Here I did 14. Things are looking closer, but my number is really large. That doesn't make a lot of sense. I'm going to go back up to 16. We'll try 16. Again, I'm really nailing it here. And my number is really large. That's 1.2 to the 10th power. That's not good, guys. So why would that be? Well, we'll get to that. Let's do this. Let's do an experiment. We're gonna go to the next box here. Now remember, I did a 16th order that looks really, really good. I happen to notice in this data that there's a gap here between like 0.2 and 0.4. So I would like to see what it looks like in that area. So I'm going to put in numbers that are like 0.2. You guys can put in numbers that you want. It's up to you. I'm going to put in 0.2, 0.3, maybe a 0.3, oops, 0.25 and 0.35. It looks like I'll kind of cover that area. So I've got some new points. You got to run that. And then I'm going to do this, all 3 of those models, and take a look at my points. So here's something interesting. You guys do this while I talk about it. So degree 1, there's my blue line. That's my model. And you can see that there's points in there that I added. It's never seen those points when it built the model. Not surprising, they fit the line really well. But it doesn't, it doesn't say anything interesting. It still doesn't seem to fit this curve very well. The second order one, boy, this still fits the curve. I'm pretty happy with it. Take a look at the 16 one. So I fit everything really well. And then look at this. It goes all over the place. All right. It is wildly erratic because it's never seen data and it's not doing a very good job. Everyone observing that? So not hearing much, I'll continue. If anyone wants to make a comment, you're welcome to.
Can you scroll back up to the points that you typed in?
Sure.
So the 0.2, 0.3, the 0.25, those are the points that you're adding specifically to the model, or trying
the ones that I'm evaluating the model at.
Thank you. Yep.
In the green. So I said, hey, I don't know what's happening in this section. Let me see what the model does. And it turns out the model is all over the place in those sections. And arguably, there's going to be other points in this range where it could be. So I've got what appears to be a good model. I fit really well. but yet it's all over the place when I start to look at points that my model didn't see. All right. So let's figure out what's going on here. Like, what is going on with these points? So here's what I'm going to do. I'm going to map out. So I said there's 3 or 4 points. I did 4 points in this range. I want to see what it looks like. Why don't I map out the whole function? Now that I've got a model, why don't I input every value of x and see what every value of y looks like? See if that makes a lot of sense. And at the same time, I know my true function, so I can look at that. So that's what this next box is. So we're going to look at the regression model, that is the function that it created, and we're going to compare it to what is ground truth. So let's go ahead and hit play, and I'm just going to talk my way down. So I've got 3-degree models. I got my first order of the line, my second order, and it turns out I did 16. And I'm going to plot all of those. All this code is a repeat of the code that we had. But right here is the key. See this? It says X test. It says, give me all the samples between 0 and 100. Let's see what happens. Now, here we've got our true function, which is in orange. Everyone should be able to see that. My samples that I took are the ones that I sampled originally and added noise to, and I fit to. Those are those blue dots, the darker blue dots. And then there's this light blue line, which is the model. So what we see is that my true function is orange, but because I used a first order model, we're not surprising, it doesn't fit very well. When I do a second order model, sure, it fits better. But what happened is I overfit in my 16th order model. Notice that I nailed my points really well on the curve. But any place that didn't see the data, I am now way off base because I fit to those particular points and was not able to generalize. All right, is everyone understanding this? Does anyone have questions?
Yeah, one question. What degree would a sinusoid be, if it really is a sinusoid?
So it turns out a sinusoid is not a polynomial by definition. You can use a Taylor expansion for a sinusoid, and it will create a polynomial that has like 3 or 4 terms in it. And I actually looked at that Taylor expansion. I didn't show it. The closest one is likely going to be about a degree 4 or 5. The closest one, so if Corey did a 4, she might see something, or a 5, she might see something that fits that really well. But it's really when you get into these very high order polynomials, we are so busy trying to hit all of our points that we can't control where we don't see the data. So what are our lessons learned here? Lessons learned here is that number one, we can't just look at the data points that we're training with. We have a problem because if we just look at those points, we overtrain. That is, we fit the points really well, but in between the points, we don't know what we're doing. We're at a complete loss. It's not really a random guess because it's fitting a function, but it's not really based on any sort of a data. And this gets into a section that we're not going to talk about today, which is the sort of the Occam's razor principle, which is the simpler the model, the better. And yet it still has to meet the goals. So any questions? Otherwise, I think I'll jump to the overfitting number 2, which kind of formalizes the language around this issue of overfitting and underfitting. No questions? All right, it seems like we're okay. No one's in a breakout room, Dave, that we have to be helping
Nope.
or anything?
Nope. I guess maybe everyone keeping up. Can we ask that in the other direction, right? A sign in the affirmative.
Yes.
How are things going for everyone?
Going fine.
I'll note the one thing I noticed, that anytime you make a change in the notebook, make sure you hit the play button for that box and then play, every box sequentially. That was one thing I caught so far.
Absolutely. Good. Okay, I'm gonna, this code base obviously is something that everyone gets to keep and use for themselves. You can play around with it more. And in fact, you know, all of this stuff is, it is an example, but it's an example that you could start to modify to your own needs. And the other, what Chris is going to show you is exactly that. He's going to really formalize how you can actually run models and do interesting things. But I am going to, before turning it back over to Chris, I'm going to open another notebook and ask you guys to do the same. Again, all of these that we're looking at are going to be in GitHub. And we're going to look at overfitting number 2. So if a couple people want to just nod when they're ready with overfitting number 2, I'll get started. Ron, it looks like you're talking, but you might be on mute. So if you're talking to us, you should unmute.
Yeah, and how'd you get back to the other file? I'd lost that.
That's fine. Under the File menu, you're going to go down to Open Notebook. From Open Notebook, you're going to go over to GitHub. If it no longer says SMNIEE here, you type that in, you do a search, and you'll see all of our code. And way down at the bottom, there's one called overfitting number 2. So here, I don't have quite as, there's a little bit of code for editing, but you know, I'm really leaving it for Chris, who's far more the expert in running models than I am probably. So let me just talk a little bit about this issue of overfitting and underfitting and what's called the bias variance trade-off. Let's start with some definitions. Chris already, excuse me, went over this. Remember, we talked about that mean squared error. That is the total error between my points in my model. However, it doesn't really say anything about the difference between any single point and the model. That actually varies greatly. If you remember, we had the one curve that went all over the place. That could vary quite a bit. And so when we want to look at that, kind of what we can do is take all those error points and we calculate the average distance between an observed point and the model's answer for that point, okay? And that is mathematically what we call the bias. Now, for me, coming my background, I actually am typically using the term accuracy. So the smaller the average distance between the points in the model, it gives you higher accuracy, okay? And we'll see this in your classic bullseye chart in a minute, right down below. Second, we have this notion of variance. So if we care about the average distance, we also care about the spread. How much variability is in the air? Are my points all over the map, or am I just off consistently? And that is called the variance. Again, for me, I often don't use the word variance. I sometimes call this term precision. And so many of you, whether or not you've used the term variance and bias or accuracy and precision, have seen charts like this. If I have a low bias, I am near my target. If I have a high bias, I'm away from my target. If I have a low variance, they pack together really tightly. All my samples are really close to where they're supposed to be. And if I have a high variance, it's a shotgun, wide pattern of samples. And of course, our goal is to be very close to the right answer, and all of our answers to be very close to the right answer. Sometimes you see a situation where you're close to the right answer on average, but individual points are all over the map. And of course, the worst is when you're away from your target. That means I say the real answer is 12 and the actual answer is 19. That's not so good. But if you ask me that question over and over again, I'm going to throw a bunch of random stuff and it doesn't make any sense. And so this trade-off, it turns out specifically in statistical modeling, it is a trade-off. You rarely can have both low bias and low variance. And that has to do with what are called random effects. There's noise in there that will always exist. You can never get a perfect bullseye. Think of it as my bowling score before and after drinks. It's highly variable across the board, and I can't control that because drinks are required when I go bowling, for example. So in this notion of model development, there's this trade-off between bias and variance, and that's directly related to underfitting and overfitting. So an underfit model, a model with very, very low complexity, is likely overly simplistic. And therefore you can't capture the variability of the actual data. You can't generalize anything. An overfit model is too complex and fits the data points, but doesn't fit the underlying general model. And so it doesn't generalize. And so what we have is this very common chart where if I have a model that's low complexity, I end up with very high bias because I don't have enough data to be very accurate, but I might have low variance. And as I get more and more complex, those things trade off. And so if you take those two curves, you come up with this optimal middle point where we're trading off the error related to bias and the error related to variance to get your total error. So this is the conceptual reasoning why we are concerned about this problem. So how do you do this? How do you hit this magic point? Well, let's consider how the data is used in a model. So we give an algorithm a bunch of input data with known output labels. We just did that in the last experiment. That training data is really great way to decrease the bias. The more training data we have, the more we can fit to it. So we can decrease that bias because we're fitting it to more and more data and therefore reducing the average error. So our training data gets us lower on the bias curve, but it doesn't generalize. We need to be able to make it general, and the only way you generalize is to have some data that the model has never seen before. Say, oh yeah, this worked or this didn't work. And we call that the testing data. So we've got training data to help with the bias or help control bias. And then we've got the testing data to help control the variance. And ultimately, we want to take and put those together in a training testing paradigm, which is what Chris is going to go into much greater detail. So we're going to do that in a really simple case. Any questions? I know there's theory and not as fun as typing, but anyone questions so far? All right, I'm going to keep moving then. This is a very, very simple model. This is the data set you can find on GitHub. It's a data set related to power plants. And they had collected a whole bunch of data, about 9,500 samples. They looked at the temperature, the pressure, the humidity, and the exhaust vacuum, and they tried to predict the net hourly electrical output of a given power plant. So this is really interesting. If I look at the environment, can I determine how much electrical energy output I need or am having from my power plant? And so I'm using pandas. We've used pandas before. It's a data frame. Think of it as an Excel spreadsheet built into Python. And one of the nice things about pandas in Python is whenever you want to load a file, you can actually pass it a web address like I did here, and it will load it directly from that web address. So this is going to read it in, and it's going to print out some information. So let's go ahead and hit play. Give it a second. It's got it downloaded and all that stuff. Okay, so as it did it, what does it tell me? It says that there's 9,600 or 9,500 entries. The entries are AT, which I think up here I note is ambient temperature. Oh, I should have put an A there. V is exhaust vacuum. AP is the ambient pressure. RH, relative humidity, and PE is the electrical output. So I have all these values, and if I take a look, this is kind of what they look like. They're just numbers. Remember, the goal here is to take all of these, AT, V, AP, and RH, and predict PE. And again, just because we've talked about a lot, I'm going to use a linear regression model. Can I do a linear combination of these, which is weighted, to get some sort of estimate of the function or create a function that predicts that? So we're going to go to the next line. Notice I'm using sklearn again. I'm going to be doing linear regression, and I'm going to bring in a new concept called the learning curve. This is helpful for understanding what's going on. So we have features. These are the inputs, and we've got our target, which is the output. And just for fun, I'm going to train on a single data point. I'm going to take a single row. It doesn't matter, randomly. I'm going to take a single row and see if that can build me a model. We're using a slightly different syntax. I'm going to take just a minute to go over it. I'm going to go over the learning curve in a second, but basically I say I want a linear regression model. That's my estimator. My X, or my input values, are all my features. My Y is my target. My training size in this case is 1. I'm going to use 1 point. My CV is what's called cross-validation, and that's training it 5 times. And that's one of the things Chris will talk about. What does cross-validation mean? And I'm going to look at that mean squared error. So I put all those things into this function called learning curve, and let's just see what it spits out. Let's go ahead and hit play. So there's not a lot to see yet. Basically, it says I ran it 5 times. My training score was 0. Well, there's only 1 point. The model is going to fit that point, that's for sure. But my validation score are these really large numbers, large as in very far away from 0. So the first time it just did an awful job, and the error was 619, and then it got down to minus 380 and kind of hung out there. So it makes sense. Why would a single point be able to train a whole model? Let's choose a different training size. I'm going to choose a size. Everyone fill in your blank here. I'm going to choose like 2,000. I'm going to run the exact same model. And now, interestingly enough, in my case, and you guys should be doing this too, is that my training scores go up because now I've got multiple data. I know I can't fit it perfectly because there's some errors, some random error, but my validation scores go way, way down. Now, instead of being minus 600 or minus 380, they're all getting close to about minus 20. Well, it would make sense if 1 is not very good, maybe 2 is better. If 2 is better, maybe 3 is better. Maybe 17, maybe, what is the right number? Anyone want to take a stab? What is the upper limit of samples that I could use to get a good answer? Anyone out there try any different numbers, and how do they come out for you? All right, I'm not seeing a lot. Oh, go ahead, please.
Say, I'm assuming you can't use more samples than what you've got, right? So
there you go. Upper limit. Absolutely. Thank you, Dave. Now with that then, because you put yourself on the spot, I'm going to put you on the spot. If you use all the samples for training, how many samples do you have left for testing?
None.
None. And if you have none for testing, what is the problem with that model going to be?
You have no idea if it's accurate or not.
That is correct. You have nothing to train it. You've done all the training, so there's nothing to test. If there's nothing to test, we're back into this exact same problem that we're way off one end of our model complexity curve because we're going to overtrain and we won't generalize, just like we saw before. You can build a more complex model and you can use more of your data points, but suddenly you're going to be overtrained. So let's actually take a look at this more generically. So what if, and it turns out you can do this in this tool, I can actually specify multiple training sizes. So I'm going to put my 1 in there. Maybe I think I'm going to add a 2 in there, maybe a 10. So we can kind of see orders of magnitude all the way up to about 7,600. You can't actually, scikit-learn doesn't let you put in all the samples because it says you can't train if you're using all your data for training. You have to have some tests. And so this is the list of sizes that you can do or that I chose. And if I hit play there, what do I see? I see lots of numbers. That's actually not very much fun to read. I'm going to, we're going to quickly look at it, but then we'll jump past it. So here are my numbers. Each row refers to my training number of samples. So 1, 2, what else do I got? Be like 1 and then 10 and then 100 and 500 and so on. And I ran it 5 different times just to see how it does. And it is true that it looks like my training score numbers go up and my validation score numbers go down. Now, again, this is a bunch of tables. It's not very good to look at. That's why we want to get into these things.
Hey, Darwin.
Hi, how's it going?
Good. Let's see here. Was just gonna ask, do you see where Holmes is at? Do you have any questions?
Yeah, I was just trying to run that one with a training size of 2000.
Okay, so
But
you
I got an
got right up.
error.
You know right where he's, or you found the
Yeah.
notebook and everything where he's at.
Yep. Yeah, I got the link. Thank you.
Oh, all right. Oh, cool.
Yeah.
Just all right. Sounds good. We can jump back over. If you have any questions,
Okay,
just
awesome.
type into the chat that you want a breakout room with somebody, and they can help you out.
Okay, thank you.
You bet. Thanks.
Grow, those two things converge. And that's a good thing. That means my training is hitting a limit that it can't really train any better, but my validation or my testing set is also hitting that limit, which means that I'm not overtraining it. And in fact, if we go a little bit further down, these are generic sort of examples of these curves that help us understand the data. We actually have this scenario where the two of them converge very nicely on the same asymptote. Adding more training data is unlikely to help in this situation, all right? We're not getting any better. And our test set is also sort of maximized. It's gotten as good as it's going to get. If I have a big imbalance, then there's a chance that adding more data or building a more complex model will work. So how do these training curves go back to our notion of bias, incorrectly spelled base, that should be bias, and variance? Well, it turns out if I have a high bias situation, okay, what we can see is a high training bias in high training error, so the number is high, indicates a high bias, whereas a low training error indicates a low bias. And variance refers to the gap between them. So I can use a simple curve like this to help me understand, is my model doing a good job? Is it complex enough? Do I have enough data sets in there? And I can use that to do the evaluation. And I'm going to stop talking because this isn't as interesting as running models, which is what we'll do with Chris in just a minute. But I do have a couple closing remarks that I'll make. We learned here about underfitting and overfitting of models, and the issue is sort of formulated as this variance trade-off. And the learning curves are really helpful to understand that. But there are some gotchas. You know, ideally, you'd like to see these two curves that we have here converge at 0. We'd love that to be 0 error, and they converge right at 0. That's just not reality. And that's not reality because every measurement you take has some natural random effects, noise, classically defined noise. You will never get, or never in real world observation, get 100% precise and accurate numbers, so you can't build a 100% precise and accurate model. So rather than worrying too much about trying to get that error down to 0, what you really want is to understand how good a model can be, which is related to how the two of them converge. And that leftover line is either because your model, you don't have the data to answer the question, or there's just noise in the data that you will never be able to predict. In addition, so these are independent points. Number 2, some advanced machine learning models are iterative in nature. I've been showing you single time point, like a single snapshot. Models, particularly when we get to deep learning models, are iterative. And so you train and then you learn from that training and you do it over and over again. Evolutionary models, stuff like that. When you run into these evolutionary kind of these iterative sort of processes, you can actually use this same plot but in a different way. Instead of increasing the training set size, this steps through in time. Model 1, Model 2, Model 3, and every model should be improving. And you'll see a same sort of convergence. So it's important to understand that these learning curves are not just about how big is your training set. You could do model complexity across there. You could do number of epochs or training iterations across there. You can use these in a number of different ways. And we haven't done that because we haven't gotten into iterative models yet. When we get into those things, then you'll see these pop up again in almost the same context. And then my third point is, so far we have been discussing regression problems. Remember, that's figuring out a statistical model that fits some sort of function. That's what we spend our time on. That's what linear regression is really good at. We really haven't spent a lot of time on classification. There's a little bit in logistic regression, but classification where you're trying to say, is this a cat standing on a dog or a fish trying to eat ice cream? You know, these are a classification problem. And again, you still use these same frameworks. The algorithms are different. A classifier does something different than a regression model, but you still use these core things around learning curves and training test paradigms. So with that, I know I've done way too much talking. I will turn the screen over to Chris and answer any questions while he moves on to showing real examples. Questions from the audience?
So not particularly related. I mean, actually, it's related to that third point. A lot of the machine learning problems that you hear about just in news or everyday situations, right, are using some sort of machine learning to identify, like you were saying, pictures or text or those sorts of things. So how do you apply the what you're saying here as far as regression training to that more classification style of a problem, or is it a completely different approach?
It's not completely different, but it might. I'll give a high level, but we'll have to, in a different workshop, cover that. So fundamentally, the tasks are different. I think we can agree on that. One is about usually continuous values. It's trying to find a function. That's a regression model. The other one are these binary decisions. Are you A or are you B? And when you get into binary decision making, you don't evaluate it by measuring the distance between your guess and the known truth. So that's what we look at, mean squared error, which is the distance between those, or the difference between those. What you look at is statements about sensitivity and specificity. Did I guess that this was an A and in fact it was an A? Or did I guess it was a B, but in fact it was an A? Or I guessed it was a B and in fact it was a B. So it's a different framework. Actually, much of the code ends up looking the same, but instead of calculating functions, you just basically are calculating thresholds, and you develop these binary metrics of comparison. That's not very satisfying. I understand that. We will definitely be getting into those very soon. But overall, what you end up doing then is those curves, instead of those curves being based on mean squared error, they're based on the area under the curve of a classifier, or your ability to guess A is A and B is B. It's just a different measurement of right and wrong, if you will. I know, not very satisfying. You can ask more, and I can try and explain it more if you.
Oh, I think that helps. I mean, you can't necessarily take a cat and make it equal to 10.7, right? So it has to be much more binary. So that helps.
Okay, good. Any other questions? All right, Chris, show us how to do this.
All right, thanks. Let's go back to the Colab and then open a notebook. Go to GitHub. Again, it's SMNIEEE. And if you scroll down, you'll see 1_train test validate. Open that notebook. It says, do you want to leave? Say yes. If you can always go back and rerun the notebooks you did before, or if you want to save it before you leave, you can do that too. So we've kind of gone through all the understanding of why we want to do these different things and what we're talking about when we say, oh, we want to train and test the model against the data. But I thought it would be good if we just took some data and just tried some stuff and played with it and kind of had a playground. And in fact, if you want, at any time, coming back to Colab, there's actually, I think it's somewhere on here, you can tell it that you want to open it as a playground. Maybe it's under open, and then it won't save any of the results. You can just try notebooks and try out different things, and it won't save any of the results. You can, like a scratch pad almost. So for this, we need a data set. I picked a data set from a online machine learning data set library from was UCI, I can't remember now, California, I don't remember. So there's a data set, and I'm going to show you how to do this the way that some people may prefer to do it if you were to do this on your own. So if you click this first link, you can try and save the file. You can save the file to your desktop. Can you guys see that save as? Does that show up? So you can save the file to your desktop. And on the second one, this is a file I created. The data set we're downloading doesn't have names for all the columns in it. So I created a file with just the names so that we don't have to type in all 147 names by hand. So you can right click that one and you can save that link to your desktop as well. So you have both files saved. So in Google Colab, you can upload files once you've started your runtime. So you go over on the right, you can click connect, and it will start the running of the session. It will connect to RAM and disk, and you'll get some temporary swap space where you can store data. So under this cell, if you run it, now it's waiting for you to choose files to upload. So click choose files, and then you want to go to the files that you, let me find mine here. So you can upload the two files, select them, click open, and I'll upload them, and you'll see the data over here on the left. And you'll see your two files show up there. So there they are. Okay, so we have our data. If you store your data directly in Google Drive, I put in a link here on how to, you can actually mount your Google Drive and point to it directly, but I didn't do that, but I left it in here for people who want to try that. Okay, so now we're going to go in and load the data and take a look at it. So you're on this first cell, it's just importing the right modules that we're going to need to use. And then we're going to import the header information that I created. So you want to run that one. And then the next cell, we're going to load the data. And then we're also going to, in the same cell, it's going to also give the column names since the data file doesn't have it already. With data frames, it's structured data saved in your program, and you can point to specific pieces of data based on a number of different reference techniques, indexes or column names or whatnot. If you want to view the beginning of a data frame, you can just use your data frame name, in this case df, .head, and it will show you the first 5 rows. So click that. So you can see here the first 5 rows of data. And this data set has city name, and for some reason they went in and put in township or city or whatever at the end of the name. You can see here row 4 is Bemidji, but they call it Bemidji City. And I don't know why they did that, but that's how they labeled all their data. And there's 147 columns, and it breaks it out, tells you about different metrics for the area that the data is collected from, by age, ethnicity, urban, rural, population density, race, how much money is spent on police officers, how many police officers are on staff, all the way at the very end, the last couple columns, it has violent, it's called violent crimes per 100,000 people per population, and nonviolent crimes per population. So those are the two key pieces we're going to use.
Question for you, Chris.
Yeah.
So I'm not getting it to load correctly, and I'm wondering if you do the load and view the data,
Mm-hmm.
and then.
So were you able to upload the files? Okay. Did that work?
Yep. They showed up in my.
Okay. So that worked.
They saved to your computer. Did they both save as text files, or did the one that's supposed to be a CSV file?
Yeah. Yeah, that's right. I forgot. Sometimes when you download it, it'll change this extension. What you can do is just go in here and change this CSV to .txt if that's what the file name is. So if you open this up more, check what this extension is. And if it's txt, just edit it here and run the cell.
Okay, that was. Yeah, that was it, I think.
And then you have to rerun all the cells after it. It's not gonna.
Yep, that was it. So I changed that from CSV to TXT, and then everything worked.
Okay. On some machines, when you go to download that data from the GitHub repository, it wants to save it as a text file, not .csv. I don't know. So rerun the cells, and then you can take a look here. And if you want, you can look through the different column labels and see all the information in here. There's quite a bit. But one thing you'll notice is this NaN pops up a lot, not a number. And what we did up here in the cell above, we told it NA values equals question mark. In the data, if they don't have a piece of data for a specific city, they put in a question mark, meaning that they don't know it. Well, we're telling pandas to call that not available or not a number, because it treats those values distinctly in a number of functions. And we passed along this information telling it, if it sees a question mark, convert that to not a number. That's why you see all these not a numbers in here. Now that can be a problem if you want to look at, say, police calls per population, and a bunch of the cities don't have any information. So you're going to have to clean up your data to do that. We'll get to that next. So down here, you want to extract the data for analysis. So on this first line, we're going to create a new data frame. But what we're going to do is take our current data frame and drop any row, that's what this drop NA means, drop any of the rows where there's not a number in any of these three columns. So these are the three columns we're going to look at. So we're just going to drop any of the rows that have not a number in these three columns: population density, nonviolent crimes per capita, and violent crimes per capita.
So let's just take a minute and make sure everyone understands why these are the ones we're doing. So if we're trying to train a model to nonviolent or violent violent crimes per population, if there's no number there, there's nothing to train against. So we really have to get away from that. And the same thing with population density, if that's something critical. So someday in one of these workshops, we'll cover what to do with data, missing data, invalid data. But what's really important here is you can't build a model if you don't know anything. And so this is a really critical step for dealing with missing data.
Yep.
Thanks, Chris, for letting me speak.
Yep, and it's a good point. And as you get into this modeling more and more, you'll find that there's more approaches to deal with missing data than just ignoring that particular sample. You may not have enough data where you can just afford to drop a bunch of samples. So in that case, there's actually other techniques that are used, or that are at least available in a toolbox for someone to look at. But because we have plenty of data here, I'm making it easy on us, and we're just going to drop those specific samples out of our data set. So now that we have a new data frame with only valid data and the categories we're looking at, I decided, well, let's take a look at what the data looks like. So in the next 2 lines here, it's going to plot some data where the X value will be either the non-violent crime or the population density. And for both of them, we'll have the violent crime on the Y-axis. And we can kind of look at what those trends might be. So run that cell. You'll see 2 plots. On the top one, you see what looks like, if you squint, maybe a linear relationship between violent crime and non-violent crime. Or perhaps it could be quadratic. You know, you may have to play with different models here. On the violent crime related to population density, it looks pretty broad, but you could maybe justify a linear regression there. It's kind of hard to tell exactly what type of model that might be. So we'll just try some stuff and see what happens. Okay, so first I thought it'd be useful if we went and actually just did some manual stuff so we kind of get a sense of what we're doing, rather than talking about these higher level functions that do all the work for us. Kind of dig into it a little ourselves just to kind of get a understanding of what's happening. So we need a couple functions from scikit-learn. So we'll run that cell. Okay, so we have 2 functions, mean squared error. We're going to use that to calculate our error, and train test split. And what that's going to do is help us split up our data into the training portion and the test portion. So down here, now I'm going to assign my data just Y and X data labels so that I can keep them straight and I don't have to remember which one is my Y and which one's my X. I'm going to label it so it's nice and clear. And I'm going to make my Y data my violent crime data. I'm going to make my X data have 2 portions to it. It's going to include the non-violent data and the density, population density data. So I'm going to create a n/2 array where n is the number of samples we have. That's being calculated up here. And in that array, we're going to have one section be the non-violent data and the other section be the population density. And that's going to be the data we're going to work with through the rest of the notebook. So you run that cell, and you see that the number of samples we have is 1902. So we have, you know, not as much data as we had on some of Dave's notebooks, but we still have quite a bit of data, which is good. On this next cell, we now need to split it up. So in here, we're going to say that we're going to take 10% of the data off the top and withhold that for our testing at the end of model fitting. And of the remaining data, we're going to use 20% of it for validation, leaving the final chunk of data, roughly 72%, for training. So by defining these 2 parameters here, you can just pass them into this train test split function. So on this line here, first, we're going to split the data, kind of like we saw in that first workbook. We're going to have train validation data and test data, and the test data is going to be withheld for the end. So we pass in our data frame or our data information, and the test size, we're going to say test %. So this amount. Now, of the data that is remaining in the train valid portion, we're going to split that again based on the validation percentage that we put here and create 2 more test sets, our training data and our validation data. You can see that on that line. And so then we'll just plot how many samples are in each of these sets at the end here. So go ahead and run that cell. You'll see we have 1368 samples in our training, so that's pretty good. Our validation set is about 343, and our final test size is 191 samples. Now you can go back and you can try different values here. If you want to put maybe 15% in there, you can do that. So try that. give it a run, see what happens. There you go. Make sense? Everyone kind of following that? So we're just letting the tool split up the data for us, but we could do this manually if we wanted. We're just saving ourselves a little time here. Okay. So,
and then that tool is just randomly grabbing the 191 or
correct.
data points. Okay.
Correct. It randomly samples from the data set and assigns it to either the test or the training sets. And then you can go in and the function has more inputs you can give it if you want to put in some more control onto how it does that splitting, but we'll just leave the defaults because it's easiest. But yes, it does select the samples randomly into the two portions. So it's not just a linear truncation, but you could do that. I mean, if your samples, in this case, our samples are random-ish. I mean, they're organized by alphabetically by city name. So there's no obvious reason why it's correlated to city name, but maybe it is. You know, that's something you could go look at. But this will take some of that unknown out of it by just randomizing the data. So we're going to try to align ourselves to the data. And so to do that, we're going to need a simple function that just calculates a line given some inputs. And this cell here, if you run it, is just going to create the function. And the function we're going to pass in is our data, so our x and our y. We're going to give it an intercept parameter. Remember, a line has an intercept and a slope, and then we're going to have two slopes because we have two x variables. So we have one intercept and two slopes. We'll pass that in, and it's going to return our error. So it's going to take our intercept and slopes. It's going to calculate y values for our x inputs, and then find the error between our calculated values and the input y's, and then return our error. So down here, we're going to define an intercept, call it b, and we're going to define our slopes as a two-dimensional array. So b of 0 and m of 1 and 1. And if you run this, you can see what your error gets to be. It's huge. But now you can try to refine it. You know, maybe you want to try, I don't know, an intercept of 100. What does that work out to be? Well, it's not much better. So let's try changing our slope. So we'll try changing that. Maybe change it to 0.4. Change this one to 0.1. See what happens. Well, it's a little better. But iteratively, we can go through and keep trying to improve this value, right? So we're calculating our training data and we're looking at the error. And as we look at it, eventually we need to look at our validation set and say, okay, if I think this is trained now, let's check it with our validation set. Okay, well, our error is still pretty large. You can see here it's actually even larger than our training data. Well, we can go back and we can try a different intercept maybe. Maybe we can try 105, I don't know. Okay, try this again. Now this iterative approach is something they've hinted at before. So typically in a multi-dimensional learning setting, what we would do is use our data in our validation, and we would iteratively have it refine. We would have the computer program refine these parameters for us using a technique. There's a number available. Typically, it'd be something like gradient descent, where you just keep trying to approach the most optimal value for these and get the best fit possible. And you would calculate the values with your training, and then you would check it with your validation data, and then you would iterate back and forth to try to minimize your error. And that's basically all we're doing here, but we're doing it by hand, right? Okay. So that's fine, but that's hard and takes a long time, and no one wants to sit there and manually do this. So let's go down and see how the scikit-learn package would do it. So just like before, we're going to use linear regression, where we create a regression model, and we're going to pass it our training data. It's going to create a fit, and then we're just going to print out what's the intercept in the slopes that it got. So you run this cell, there you go. The intercept is minus 238 point some, and the slopes are about 0.14 and 0.045. So I wasn't very close, but you can kind of see how iteratively you could have got there. If I wanted to keep trying values, maybe I could have gotten close. I don't know. So now that we have a model, we're going to see how good that model fits our validation data. Remember, this is the data that we would use to then go back and refine the model if it's not optimal yet. So you see here that our error is still pretty high. So we could go back, we could re-split our data, we could run this whole process again and see if, I don't know, maybe we could do better if the data is split differently. But we still have our test set, and this is kind of our gold standard set. Not that it's anything special, but the fact is that we don't use this information to go back and refine our model. That's what the validation data is for. So we check this one, and this error is even worse. Can you guys still hear me? My headphones died.
Yes.
Okay, good. All right. So, sorry about that. So maybe we should try a polynomial, much like what Dr. Holmes showed. We're going to try a polynomial. Here I just set up a quadratic polynomial, degree of 2. We're going to repeat the process. Now, when we do this, what scikit-learn is doing is it's creating all the terms in a multi-dimensional quadratic. So you'll have your x1 squared, your x2 squared, but you also have your x1, x2 term in there as well. So we're going to run all this, and all we're doing is fitting a multi-dimensional quadratic equation to the data to see what happens. And then we'll, down here, we'll look at what the mean squared error on the training set is. So you can see that it's probably, it's about the same as it's been. It's not really that much better. So we'll try it again though, but this time we'll run the model on our validation data and our test data and see if those results look any different. And no, I mean, the validation data is a little better, but ultimately the data is still not fitting real great. And at this point, you would say, okay, well, maybe I need a different model, or maybe I need to go back and look at a hybrid model where I split the two parameters apart. Well, you know, this is part of the whole process of creating models, is assessing, is your model doing what you need it to do? And clearly we're still getting a lot of error. But there's another thing we can try. We can try what's called cross-validation. I'm just going to talk about what's called k-fold cross-validation because it's a kind of simple technique, but it explains how the process works. In cross-validation, what you want to do is you want to iteratively take your data and split it into two groups, your training and your validation set, and then kind of try all the permutations of different ways of splitting up the data. In k-fold validation, what we do is we take the data, we break it up into a number of folds, let's say 5, and then we run our process where we assign each chunk of the 5 chunks of data to the validation set and the remaining chunks to the training set. So for the first iteration, perhaps chunks 1, 2, 3, and 4 are training, 5 is validation. And the next time we run 1, 2, 4, and 5 might be training, and 3 might be validation. And we run through all those permutations and look at the results. So scikit-learn makes this a little easier on us. It's got it built in where it can split up the data for us. So on this cell, you can kind of see where we're going to go with this. So on this next one, we're going to specify the number of folds we want to try. And this is where we're going to kind of play with it a little bit. We're going to create a model for that number of folds. We're going to create an array where we're going to store our error. And then we're going to iterate through the permutations of this fold and record our error for each of the permutations that the folds are going to run. So if you run this, it's going to have 5 permutations because we set it to 5 folds, where it tries each of the chunks as the validation set and the rest of the training set. And we're just going to record the error. Now, we're kind of interested, okay, well, what does the error look like? So we're going to have some data, and we're just going to plot the error versus the permutation. And you can see here that the error changes as we split it up. This is because as you split your data up, you're going to get different fit to it. Some data may fit better than others. But by doing this, we can see how the data is dependent, or the model is dependent on the chunks of data that it gets. So let's go back and try it with different number of folds. Let's try it with, say, 20. I don't know. Try whatever you want. Then we will run the next cell again. Boom. See all that? That's what we're trying to address with some of this. Each one of those dots, you know, is one permutation, and different permutations. We have one here that's really high in error. So we'll go and look at it now. If we redo this, we're going to create an arrays now where we're going to store the intercepts that it calculates and the slopes it calculates. We're going to plot them and kind of take a look at how those are changing with these different folds. So run this, see how the intercepts are moving around. Then you can run this to see how the nonviolent crime slope is changing. And then you can run the next cell, look at how the population density slope is changing. So on all these, if you kind of squint, you think, well, I could probably draw a line horizontally, kind of like an average, and put it through there and see how good my fit is. And that's where we're going to kind of pull this together. So in this last one, what we're doing is we're taking the average of all the intercepts in our intercept array. We're going to take the average of the slopes. We're going to use that for our model. And the way we do that is we create a new regression model. We're going to then tell it what the intercept and slopes are. And then we're going to see what the error is. So down here for the final error, we're going to take our slopes and we're going to give it our test set, our golden test set that we save for the very end, and just see, you know, how did our error do? Well, it didn't do much better than the subdivisions, but you know, that's, like I said, we probably have to go back and take a look at our data a little more and see if we find a better model. But that's the process you go through, and then you've got to iterate. You've got to check your data, and you've got to see if your model's doing what you want, because there's all sorts of models that can be used. And this is just one example, because linear regression is probably the easiest one to describe. So with that, I don't know if anyone has any questions. Anyone have any issues running this workbook? No? Okay. So that's the end of what I have on this. Feel free to take these workbooks. If you go over here, you can download it to your desktop. If you have a Jupyter notebook installed, you can save a copy in your Google Drive if you want. You can
always download it, and then when you go to open a notebook, you can upload one. Click on upload and uploaded notebook if you have one on your desktop system, and you can sit and play with it. You can go grab different sets of data. This website I got the data from has all sorts of data available. You can go there and I'll just take you there. There's all sorts of sets that you can go look at. You can play with them. You click on this, you can say, okay, I want regression and numerical. Then you can start looking at the different types of data it's got available. If you want to do bar crawls or air quality, all sorts of stuff. And you can go back and try to build your own models based on the same kind of approach. And as you dig into it and you learn more, you'll see that there's all sorts of tools already available to do a lot of this work for you. And you just have to learn more and more about how to apply them properly, because there are a lot of gotchas. But this is kind of a introduction to the importance of the train, test, validate methodology, which is a little more, which is building on the regression stuff we've covered in the previous workshops. So if there's any questions, we can answer those. Otherwise, I'll turn it back over to Dave to wrap it up.
Seems like there ought to be a lot of good agricultural data from the Midwest, huh?
Yeah. Yeah. Well, I didn't put it in here, but the Minnesota, the Star Tribune has been recording Minnesota's reported COVID data each day to a GitHub repository. And if you want to go grab that, you can play with the COVID data and look at different trends.
Can you
That's kind of interesting.
Can you take that data and then figure out how Minnesota or how the U of M model ended up being so far off?
Well, you could try. I don't know enough about their model, but that model is also available on GitHub. You can go learn about the GitHub, or learn about the model on GitHub and give it a shot, see if it works. But no, unfortunately, the Star Trip data just takes the reported information on the health website and records it. That doesn't have the raw data, whereas the University of Minnesota has access to the raw data, which would actually be nice to have. But if you like playing with data, there you go. It's all sorts of ways you can use it.
Very cool. Thank you.
If I may, it would be really helpful, as we've done in the past, try and get some feedback from everyone. If this is the type of topics we're interested in, if we're moving at a good pace. We know we have other topics we want to cover. Just so you know, that broad list would include classification, which is something we talked about briefly earlier. Different machine learning techniques like random forest or gradient boosted machines, ensemble learning. Deep learning is obviously one, but that's a whole series of lectures around deep learning, or those. There's clustering and unsupervised classification we haven't spent time on. There's dimensionality reduction, feature engineering. So plenty of things we could talk about, but we want to make sure this is useful to the community. So if anyone has any feedback about the lectures we've done, about the pace that we're going, we'd really appreciate that. Even if you want to send it confidentially to Dave or anyone else, you can do that, and that'll get back to us. So anyone want to comment online right now?
I thought it was great. I only got lost once, so I appreciate it. I'm enjoying this whole series.
Yeah, and with that Google Colab stuff, you can do all the notebooks right there on their servers. You don't even have to have anything installed. Just web browser and you're off and running. So it's pretty handy. Of course, they'll sell you on more power if you want a big machine to do something, but you don't need it.
Yeah, I thought it was very good too. I like the speed. It doesn't seem like you're trying to impress us too much with your your level of knowledge versus mine. So I appreciate that.
It's a big assumption that I actually have a level of knowledge.
Yeah, exactly.
This is Dick Hedger. I'm a newcomer to this group. I thought it was very good. I wanted to learn more about machine learning. I thought that if you kind of send out the setup instructions ahead of time, it may help you, a new guy like me, get going earlier.
Okay, good.
Good to know.
Yeah, this is our first time with Colab, and I think having now done it, thank you to Chris for the idea and Brian for helping facilitate. I think that we will be able to do that. So that's a great suggestion.
All right. Well, if there's nothing else, we will put the recording out on YouTube. I'll try to get that done in the next day or so. Other than that, I really do appreciate those that attended, and spread the word that it'll be out there, and let those that, like I said, we did get a really good reception of these in the past, and I actually thought it worked really well, better than I was expecting, honestly, through the with this using Zoom. So I wasn't too distracted or disadvantaged, I don't think, compared to doing it in person. So yeah, thanks to Dave and Chris, and for giving this a shot.
Yeah.
So
Yeah, thank you.
with that, if there is nothing else, again, I thank you for your attendance, and we'll call it there.
All right. Have a good night.
Yep. Thank you.
You.
Thanks, everyone.